Okay, so I just started recording. The discussion today is going to be on separation of variables to solve problems, Laplacian equation, Laplace's equation in spherical coordinates, and I will do a few examples. Okay, so to remind you again, the whole idea of separation of variables is that if you are looking for the solution, like electric potential, which is function of different variables, in this case, in a spherical coordinate, it's going to be r, theta, and phi, then you can separate them. So we basically look for the solutions that can be separated into different functions, each function being function of only one single variable. So in this case, r of r, theta of theta, and phi of phi. Okay, and not all the solutions fit in this sort of category, but some solutions do fit, and when it works, it's going to be it's beautiful. Okay, I told you before. Okay, so our discussion for a spherical coordinate was focused on a situation that we have azimuthal symmetry. Okay. And with azimuthal symmetry, technically, we don't have any dependence on phi. Everything is symmetric with respect to phi, so we can get rid of the last variable. What we are working with are potentials that are function of r and theta, and they can be written as in terms of r and theta of theta. Okay, and we said if we use this. Okay, so I'm going to skip multiple parts because we discussed that before. But if we use this in the Laplace's equation, we will get two different ordinary second order ordinary differential equations. And the general solution of those for the r component is a times 1 over a times r to the power of L plus b over r to the power of L plus 1. And the solution for theta components is PL of cosine theta, where PL is the Legendre polynomial in the order of L, and it's in the variable of cosine theta. Okay. So Legendre polynomials are actually the first few terms are very simple. P0 is just 1, is a constant. P1 is x. P2 is 3x2 minus 1 divided by 2, and so on. The equation for order number L, of course, in function of x, is 1 over 2L, L factorial, d over dx to the power of L times x2 minus 1 to the power of L. Okay, so these are the Legendre polynomials. At the end, depending on what order is, you have one polynomial function, okay, and that's exactly in the order of the Legendre polynomial. Okay, so this looks a little complicated, but if you really calculate this, you are not getting anything more complicated than just polynomials. Okay, so the theta component is the Legendre polynomial in the variable of cosine theta. Okay, so for all x here, you can put cosine theta. Sounds good? So the combination of the two means that the general solution for potential as a function of r and theta can be defined as a linear combination of these over different L values. Okay, so that means you can do sigma L starting from 0 to infinity. The R component gives us AL R to the L. Second term is BL R to the L plus 1 times PL cosine of theta. Okay, and then if you look at this, we have only two fitting variables here, right? We have two fitting variables. One of them is A, the other one is B. Okay, so at the end, everything in terms of R and theta boils down to finding what AL values we should choose and what BL values we should choose. And choosing them means we need to fit and meet the boundary conditions. Okay, the general solution, the way it is, it definitely satisfies the Laplace's equation. So the rest of the problem is only finding the AL and BL values to fit and meet the boundary conditions. Okay, so we did one example, okay, and the example was one sphere that we had the potential specified on the surface of the sphere, and then we wanted to look at the potential inside. Okay, so I'm going to do another example, very similar situation in terms of the geometry and everything. The only difference is that we are looking for the case that we have that same sort of sphere, but we are looking for the potential outside the sphere. Okay, so the example I want to do now is the example 3.7 of the textbook. We did example 3.6 on Thursday last week. Let me see. Yeah, this is 3.7. Cool. So I'm going to get rid of these. And I just want to keep this. Okay. So example 3.7, which says we have a sphere and potential is specified on the surface of the sphere in terms of V0 of theta. Okay. And the question is, what is the potential outside this sphere? Okay, so this is the question. Previously, we looked at the potential inside the sphere, right? So now, the very starting point here, if we want to use the method of separation of variable, is to start from this. Okay, and we want to look at the boundary conditions, and then we want to look at the variables we have and see what we can do to simplify the general solution and narrow down all the variables and everything. Okay, so now what are the boundary conditions here? One boundary condition is, of course, on the surface of this sphere that the potential should be V0 theta. Okay, that is specified by the problem. And the other one is if we go far away from this sphere, right, potential should be 0. Okay, so as you go further and further away, potential should decay. And at V, so at R's, at the limit of R going to infinity, potential must be 0. Okay, now if you look at this general solution, right, the first term is AL times R to the power of L. L is either 0 or infinity. Okay, so if R goes to infinity, right, the first term is going to vanish. And so because of that, we're going to drop all the potential values, okay, all the AL values that create infinitely large potential at when R goes to infinity. Okay, so because of this, we drop all the ALs, and ALs are 0, and that makes the general solution a lot more simple. VR theta is BL over RL plus 1, PL of cos theta, and the L runs from 0 to infinity. Sounds good? Is it clear so far how we are approaching the problem? Right? So it's important that at the beginning you want to focus on what we have in terms of the definition of the potential and boundary condition and whatnot. Okay, so you first want to analyze what the problem is telling you. So in this case, potential is on the surface specified. Nothing at infinity is specified, but we know and understand that if we have potential specified here and nothing else is happening beyond the sphere, then potential should decay and decrease and go to zero at infinity. Okay, so with that, then you're going to look at the general solution you have and see how you can simplify this. Okay, so with this condition, potential being zero at infinity, we could get rid of AL because this is going to create potential that blows up at infinity. Okay, and that really simplifies the general solution. And now we have one single fitting variable. Okay, so if we think about the BL values should be chosen in a way that it can fit the boundary condition on the surface of this sphere. Okay. Last week we said a nice thing about the Legendre polynomials is that they are orthogonal to each other if they are not in the same order. And that is very similar to the sine and cosine functions. Okay, so that means we can create Fourier series based on that and find BL values in the same manner that we used to find the coefficients where we had the Fourier series or potentials in terms of sine and cosine of theta. Okay, so mathematically to put it down, the integral of PL x, PL prime x dx from -1 to +1 is always 0 if L is not equal to L prime, and it's 2 over 2L plus 1 if L is equal to L prime. Okay, and this is nice because now if we take this one, okay, and if we multiply it by PL prime of cosine theta, right at R equal to the radius of the sphere, then we can find values of BL. Okay, I'm assuming that the radius of the sphere is capital R. Okay, so if I rewrite this for R equal to capital R, the whole thing, the whole summation should be equal to V0R. Okay, and that means, let me get rid of this. That means on the surface, we have something like this. We have summation from 0 to infinity BL RL plus 1 PL cosine theta. This summation should be equal to V0 theta. Okay, so R equals R takes us to the surface of this, and we know that the potential is specified at this. Okay, now I want to use this characteristic orthogonality of the Legendre polynomials where I multiply this by PL prime of cosine theta, okay, and I integrate it in this, you know what, PL prime cosine theta sine theta d theta, so that the cosine is, I must change the variables from x to cosine theta. Okay, so I multiply it by this, and that should be equal to V0 theta sine theta d theta. The integral, I'm going to integrate that for theta equals to 0 to pi, and here theta from 0 to pi. And the integral from 0 to pi in terms of the cosine theta variable basically moves us from -1 to 1 in terms of PLX. Okay, so with this one,
Professor, I have a question.
sure.
Sorry, why you're not multiplying by PL prime on the right side?
In fact, I should be. I just
Okay.
missed that.
Thank you.
Thank you. PL prime cos theta sine theta d theta. Sounds good? Thanks for catching that. And now the whole integral here, okay, is a line term inside this bracket, but the whole integral here is always 0, okay, unless L is equal to L prime, and then that is 2 over 2L plus 1. Okay, so now the summation we have here from 0 to infinity, every single term of the summation is 0, except for the one that L is equal to L prime. And that makes the integral being 2 over 2L plus 1. So what we have from the whole left-hand side is BL divided by R to the power of L plus 1 times 2 over 2L plus 1. Okay, so this is the first term here. And this is the term from the integral when L is equal to L prime. So in fact, I better use L prime here. And that should be equal to that integral on the right-hand side, which is from theta 0 to pi v0 theta PL prime cos theta sine theta d theta. Okay, now technically you have BL prime here. You can move all other variables to the other side and find BL prime as a function of known parameters, not looking simple, but everything is known on the other side. So if I do that, we get 2L prime. So this term is going to give me 2L prime plus 1. And this RL prime plus 1 goes to the other side. That becomes R prime plus 1 times this. And this is basically the BL prime values, okay? So now everything in this equation is L prime. I can just get rid of the prime and make it BL so that visually looks simple. And this is now the BL values as a function of the potential on the surface and the Legendre polynomials and integral and everything. So this combined with this summation is going to give us a potential that satisfies the Laplace's equation, satisfies the boundary condition at infinity, and also meets the boundary condition on the surface. Okay, now it looks a little complicated and long because V0 theta is very general function. If we had better idea of what V0 theta is, we could narrow it down further. But the way it is, everything is known on the right-hand side, and then we can extract and calculate, obtain BL values. And in combination with this summation, that really will satisfy and meet all the requirements in terms of the Laplace's equation and all boundary conditions. Sounds good? Any questions?
How come you could take off the prime?
If you have equation that there is no L and everything is L primes, you can just switch to L, right?
Okay.
Because everything on the left-hand side and right-hand side was then in terms of L prime.
Okay, but wouldn't they be two different values?
Not necessarily at the end, because this L prime, we're going to test that for 0, 1, 2, all the way to infinity anyways, right?
Oh, okay.
So as long as they have the same range and there's only one of them present in the equation, you can just switch that.
Okay.
I mean, you could switch that to M or N or anything else.
Okay.
Sounds good? So here I really want you to become familiar with the whole workflow of how you want to look at the equations and how you want to look at the problems. Okay, the first part is identifying what you have, what are the boundary conditions and everything, without worrying about the separation of variables. And then once you want to use the separation of variables, you don't really need to go all the way to the fundamentals and write Laplace's equation. What you can do is that you can look at the general solution, which I had on the board somewhere here, okay? And then see how you can simplify that based on the boundary conditions you have, okay? Sometimes there are simpler steps. You can easily get rid of some of the constants. Sometimes it's really boils down to fitting boundary condition using the Fourier transform and so on. Okay, so I'm going to do a couple of more examples. Okay, I'm going to do now example 3.8 and 3.9. Hopefully we can do, yeah, probably yes. We can do all these of these, and then we will be done with separation of variables. Okay. Again, any question from this? No? Okay. If you hear a bit of noise, that's a heater in my office. It's pretty cold here. I try to avoid turning that on because of the noise, but now it's getting impossible. Okay, so I'm doing example 3.8. Oh, this is a beautiful example. This is very nice. This is an uncharged metal sphere in a uniform, in an otherwise uniform electric field. No? So imagine you have uniform electric fields in space. Okay, this could be kind of field that is created in a capacitor, but imagine this is in the space and goes all the way to infinity. Okay, now what you do is that you put one conducting sphere in the middle of this. Okay, you put a conducting sphere in the middle of this. And then you will get some induced charges on the sphere, right? So can you guys tell me just qualitatively what happens to the sphere and what kind of electric field and field lines we get when we put this sphere inside this uniform electric field space? The field is pointing upward.
Shouldn't it like go towards the sphere, around, and then back out?
Yeah. Let's first look at what kind of induced charges we get on the sphere. Field is positive this way, right? So probably it's going to push positive charges to the other side and negative charges here.
Yeah.
Right. So we get negative charges here and get positive charges on the top. Okay. And now, how do the field lines look like here? It's going to be always perpendicular to the surface of the sphere, right? Because you have a conductor, right? Always on a conductor, the field lines are perpendicular to the surface. Okay, so very close to the surface, they are perpendicular. As you go away from the surface, right, what happens? As you go away from the sphere, it's going to be more like a uniform field that we have, right? So far away, it's uniform. And as we get close to this, they are perpendicular to the surface. So it means they have shapes like this. And then the same thing goes all the way to the top as well. Okay. And on the sides, maybe it feels like this. Looking good? So we got these field lines here, negative charges on the bottom, positive charges on the top. Sounds good? Okay, so now the question is, we have this situation, the field would have been uniform without the conducting surface, but now we put the conducting surface. The question is, what is the potential in the space, which will be potential as a function of the radius, distance, r, and theta. Okay, so we are assuming that this is the center of the coordinate system, and we are trying to find potential as a function of r and theta. Okay. By the way, you know inside the conductor there is no electric field, so E is always 0 here. Sounds good? Okay, so now looking at this problem, okay, we know outside the conductor potential should satisfy the Laplace's equation, for sure. There is no charge distribution whatsoever outside. And then we're gonna look at the boundary conditions. Okay, so we got two boundary conditions here. The potential on the surface of the conductor is constant. So we are assuming that the V at the surface, where distance to the origin is r, the radius of the sphere, V of r and theta is 0. Okay, so this is one boundary condition, and the other one is that if we go far away from this conducting sphere, the potential is the potential 0? It's a good question. So a lot of times the assumption is that if we go far away from the charge distribution, the potential becomes 0, right? So now in this case, this is very special case because you have uniform parallel electric field going all the way to infinity. Now, I'm asking, is the potential at infinity 0? It can't be 0 because we have continuous uniform electric field, okay? So it doesn't become 0 per se, but the behavior of the potential becomes like the behavior of the potential when there is only parallel uniform electric field, no conducting surface, okay? So at infinity, at r goes to infinity, potential V should have the form of negative. Imagine a field magnitude what used to be E0 far away from the surface, okay? So if I far away from the surface is 0, it's going to be negative E0 times the distance here that I'm choosing Z. Okay, so I'm assuming that Z direction is the same direction as we have these field lines. Okay, so potential at far away from the conducting surface should be negative of E0 times Z. Okay, and Z in spherical coordinates is R cosine theta. Right. So two boundary conditions. Number one, on the surface, potential must be 0 always, and at infinity, when we are far from the conducting surface, the potential should be E0 times Z, which is E0 times R cosine theta. Okay, so this is boundary condition number 2. Okay, so this is what we have. This is the physics of the problem, the potentials, the boundary conditions. Okay, now we want to look at the general solution that we have after separation of variable. We said V of R and theta should be right, is in the form of summation from L0 to infinity. Two terms we had, AL R to the power of L plus BL R to the power of L plus 1. These are the terms from the radius dependent function, and then multiplied by PL of cosine theta. Okay, so this is the general solution. And now we want to look at what we have and try to match this, right? So cool. Okay, now first look at the first boundary conditions. That means if r, the radius is equal to the radius of the sphere, okay, the radial distance, if the radial distance is equal to the radius of the sphere, the potential must be 0, okay? Now what we have here is some r-dependent term multiplied by the Legendre polynomial, okay? And if we want to keep it 0 at all theta values, that means this coefficient combined, these two terms must be 0, right? At r equals r, okay? Meaning that if I separate this, okay, for all values, AL, capital R to the power of L, plus BL, capital R to the power of L plus 1 must be 0. Okay, so this is the only way we can ensure that at every theta, okay, at every theta, potentially 0 on the surface. Okay, so now if you look at this, R is known, is a radius of the sphere. This equation kind of relates AL and BL values to each other. Okay, so instead of two fitting variables, eventually we will have one fitting variable and the other one in terms of the other one. Okay, so this means all the BL values can be written in terms of negative AL R 2L plus 1. Sounds good? So out of the two fitting variables we have, now one of them, BL, can be written in terms of AL and capital R. And that means this simplifies in the form of sigma L from 0 to infinity AL R to the power of L. So this is the first term. For the second term, I'm writing BL in terms of AL and R to the power of 2L plus 1. That is negative of R to the power of 2L plus 1 divided by R L plus 1 times PL cosine theta. Sounds good? So if you look at this solution so far, this first of all satisfies the Laplace's equation for sure because it's coming from that general solution. And it satisfies the first boundary condition the way we wrote BL in terms of AL. Okay, so the other boundary condition that needs to be satisfied is when we are far away from the conducting surface, and that is at R equals to infinity. Okay, so we should find a way to satisfy that as well. The nice thing is that when R approaches to infinity, the second term here becomes negligible. Okay, this term becomes small, so we can only focus on the first term and try to find AL values for different L values like A0, A1, and A2, and so on. And if we find that, we can sub it back here and find the complete solution. Okay, so I'm going to say here, I'm separating this. I want to say at R, when it goes to infinity, what we have is V of R and theta equal to the summation here, AL R to the power of L times PL cosine theta, okay? And that should satisfy this boundary condition, and that is negative E0 R cosine theta. Okay, so this is what we have at R approaching infinity. Okay, now something is very interesting here because the form of the boundary condition that we have is in the form of one of the Legendre polynomials. Okay, so the cos theta itself can be written as P1 of cos theta. If you remember the polynomial, the Legendre polynomial order 1, in terms of x was just x. In terms of cosine theta, it's going to be just cosine theta. Okay, so now what I want to do is that I want to replace this cosine theta and say this is P1 cosine theta. Doesn't look more simple, but it's helpful because here we have the summation in this term. We have summation over the Legendre polynomials, and we have summation from 0 to infinity all the way. Okay. Now, if you look at this and if you want to try AL values to match the right-hand side, this gives us a very nice clue because it tells us that it's enough to only keep one of the terms, and that's term number, order number 1, that is A1, and we can set all the rest at 0. Okay? That means in order to meet the boundary condition at infinity, it's enough for me to say that A1 R times P1 cos theta should be equal to negative E0R P1 cos theta, okay? And that means we can set A1 equal to negative E naught. Okay, so we can set A1 equal to negative E naught and the rest of A values being just 0. Okay, meaning that if we set A0 equal to 0, A1 equal to negative E naught, and A2 0, and the rest of the A values until infinity, all the AL values equal to 0. So this is the only non-zero term for A's. And looks like that single term can fit the boundary condition at infinity. Okay. And with the form of equation we had already here, we were already fitting the first boundary condition on the surface of the sphere, right? So very nicely at the end, all the summation just disappears. We can work with one single term, okay? That means the final solution is gonna be not in the form of this summation, but only one A1 value, and that is negative E1. Meaning that, we're going to get rid of this so that we have a space here. Meaning that V of R and theta becomes, I don't need to use this summation, where is it, here. I just need to use negative E naught for A1. And here I have R, and only first term. And then for the second term, I have negative R3 over R2 times cos theta.
Sorry, Professor, sorry for interrupting
Sure.
again.
No.
Why are you multiplying by P1 on at the bottom right?
The bottom right, I'm not multiplying by P1.
Well, yes, on that one.
Here
that
we
one.
have cosine theta, right? So I just switch cosine theta with P1 cosine theta. P1 cosine theta is cosine theta.
Got it.
Okay.
Okay.
And it doesn't look more simple, but the nice thing is that now I can match this P1 with the coefficients of the Legendre polynomials I have on the left-hand side. And that tells me just order number 1 is enough to match this, and I only need A1, and I can set the rest of A values to 0, as I listed here.
Got it.
All these are going out of the book. But
Thank you.
But this is the only non-zero term. Okay. And if we have only one non-zero term, the whole summation over L just disappears because we have one term, and the potential at the end becomes less. Okay. Now, this potential has a very nice one. If I want to separate this term and make it completely into two terms, the first term is E0 R cosine theta. The second term is plus E naught R3 over R2 cosine theta. Okay. And if you look at these two terms, this first term is exactly the potential created by a uniform electric field in space. Okay. So this is the contribution from the uniform E0. And the second term is the contribution from the sphere and the induced charge on the sphere. Okay, so this is contribution from the induced charges on a sphere. Sounds good? So let me get to it.
Professor?
Yes.
When you write it down, when we have like when we have the PL cosine theta, is it PL of cosine theta?
Can you repeat, please?
Like when we have PL parentheses cosine theta, does that mean that like we're plugging in the cosine theta for PL, or is it just PL times cosine theta?
No, when we write PL cosine theta means instead of x, use cosine theta.
Okay.
Right? Like for instance, if the second order P2x is 3x2 minus 1 divided by 2, that means P2 of cosine theta is 3 cos 2 theta minus 1 divided by 2.
Gotcha. Thank you.
Sounds good? So now there's one more thing we can calculate, and that is very interesting. We said we have all these negative and positive charges on the surface, right? And you know it's not uniform charge distribution. Probably you have more charges on this tip at the bottom, and then density of the negative charges decreases as you move up here. Zero somewhere right in the middle, and then it's going to be positive on the other side. Okay. So if you know the potential as a function of radius and angle as this one, you can take the derivative of the potential and calculate surface charge density. Okay. So we already talked about how the potential is related to the surface charge density for conductors. Now I'm going to repeat that the sigma, the surface charge density is negative of V naught dV over dr. Okay. And in this case, we're going to look at this derivative at r equals capital R, and that is right on the surface of the sphere, right? If you look at this, we're going to calculate. If we calculate this, we're going to find the surface charges, which is the Indian surface charges. Okay. So the derivative is only with respect to r. So the terms we're going to get is from the first term we get negative E0 cosine theta. From the second term we're going to get negative 2 E0 R3 over R3 cosine theta. Okay, so this needs to be evaluated at r equals r, right? So we have a negative sign here, negative sign with this negative sign becomes positive, okay? And then we have a negative sign here again. The negative sign here is from the R2 being in the denominator, giving me a negative 2. With this combined, it becomes positive again. Okay. So these combine at R equals R. Here we get R3, capital R to the power of 3 that cancels out with the other one. We get two terms, E naught cos theta and then 2 E naught cos theta combination. It becomes 3 epsilon 0 E naught cos theta. Okay. By the way, I have an epsilon naught coefficient here as well. So this is the sigma surface charge density as a function of theta. Okay. So now we can check what kind of positive or negative charge density we are getting. At the bottom, theta is near pi, so we get negative charge density here. At the top, theta is 0, we get positive charge density. Sounds good, and that seems consistent with what we intuitively expected from the charge induction. Sounds good? So you see a lot of times at the end, what you have, of course, we start with very general solution for the Laplace's equation, but if you fit all the boundary conditions, at the end it becomes simple, right? So the potential becomes relatively simple, and then we look at the surface charge and see that becomes relatively simple as well. Any questions? Cool. Shall we do one more example? Okay, so I'm going to do example 3.9, which is a case that we have a sphere, we have a spherical shell, and we have the surface charge density specified on the surface, and we are trying to find potential based on that surface charge density. Sounds good?
So was this problem the other way around?
This problem was you put the surface inside a uniform electric field. So you don't have really any idea about what surface charge density you have at the beginning, but you have the potential specified at the surface. And the potential is combined with the potential created by the uniform electric field. Okay.
Okay.
So the other examples I did, 3.6 and 3.7, were situation that you had a sphere and potential was specified on the surface of the sphere. So these examples have similarity to each other and differences as well. So they are a little bit different. In the last one I'm doing, you don't have potential specified on the surface, but you have surface charge density specified.
So the charge density we get, that's on the surface, right?
Can you repeat?
The charge density?
Yes.
That's on the surface?
Is on the surface, yeah.
Okay.
Imagine that a spherical shell and you have those charges right on the surface.
Okay, thank you.
Cool. So we can treat them on all the surfaces here. Right, so this is 3.9 that have a sphere. Oh my God. Sigma theta, the surface charge density is specified on this chart. Okay. And now the question is, what is the potential inside? And what is the potential outside the surface? Okay. So we are considering the radius being r, capital R. Okay. So now we have a situation that we are looking at both inside and outside the sphere. Okay, and if you remember the general solution, we are in theta. The general form had A coefficients, A times R to the L, PL over R, L plus 1, times PL, cosine theta, okay? And in all the examples we did before, we said that in cases that we are looking at inside where R goes to 0, we need to drop the BL terms because we don't want the potential blow up in the middle of the sphere. And for cases that we are looking outside where R goes to infinity, we drop the second. Okay, so now the general form for inside potential VE should have the form of L from 0 to infinity. Inside, R goes to 0. We don't need the second term because that makes the potential go to infinity. I keep it the same way as AL. R to the L, PL, cosine theta. And then outside, we from 0 to infinity, B L of R L plus 1 times P L of cosine theta. So these are the general forms of the potentials we have inside and outside. Okay, both are derivatives of this one. One of them only includes the first term, and the other one only includes the second. Sounds good? So now these two should match on the surface. That means at R equals R, V in should be equal to V out. Okay. If you're on the surface, the potential should match, should be continuous. And if you look at this, that means we should match all the AL and BL values in a way that AL, R to the power of L, this is the term coming from the potential inside that should be equal to BL times R to the power of L plus 1. And that means any BL value should be equal to AL times R to the power of 2L plus 1. So this is what we get from matching the boundary condition on the surface. So BL and AL are not really independent. They are dependent. They are connected to each other with this approach. Okay. So I can technically rewrite this one, and for BL I can use AL times R to the power of 2L plus 1. Okay, so now if you look at this, the whole problem boils down to finding the AL values. Okay, with this format, the potential is matched on the surface, okay? And then if we can find AL value to match the rest of the boundary conditions, we are good to go. Okay, so the next boundary condition comes from the surface charge distribution, okay? So since we have this surface charge density, right, we should have discontinuity in the derivative of the potential. Or in other words, we should have discontinuity in electric. Okay, so we should find the AL values such that it reflects that discontinuity as well. So if you look at the discontinuity equation, V out dV out over dR minus dV in over dR, okay, that R equals R should be -1 over epsilon sigma theta. Okay, so the first term is the derivative of the potential outside the sphere as a function of R. The second term is the derivative of the potential inside the sphere as a function of R. Okay, so the difference between these two should be proportional to the surface charge density. Okay, now that means we should look at the derivative here, we should look at the derivative here, and look at the difference between them and try to find AL values that match this. Okay, so taking the derivative of this, the first term, okay, we get negative sigma L plus 1. So negative L plus 1 comes from the derivative of this times AL R to the power of 2L plus 1 divided by, we are looking at the derivative at R equals R, so here we get R times L plus 2. Okay, since we get the derivative, now we are getting 2 times L cosine theta minus sigma. Now we are looking at the derivative of this L AL R to the power of L minus R to the power of L minus 1 times theta cosine theta. In both cases, L runs from 0 to infinity. L runs from 0 to infinity. Okay, this should be -1 over epsilon 0 sigma theta. Okay, so now we can combine these. Okay, so both of them are in terms of PL cosine theta and AL as well. If we look at the combination, we get sigma from 0 to infinity 2L plus 1 times AL times R L minus 1 times PL cosine theta is 1 over epsilon 0 sigma of theta. Okay. Now, if you look at this, we have everything in terms of L. We have AL values that we need to determine, and we have PL here. Okay, so we can use the same trick. We can multiply left side and right hand side by PL prime cosine theta sine theta and integrate that from 0 to 2 pi. So I'm going to add PL prime cosine theta sine theta d theta, integrate that from 0 to pi. And on the right hand side, we had one over epsilon sigma theta, I'm going to multiply that PL prime cosine theta sine theta d theta as well. Okay, so same limits from 0 to pi. Okay, now if you look at this, this is the integral that becomes always 0 except when L and L prime are equal to each other. Okay, so out of this, we only get one term. Okay, so I'm going to get rid of the whole thing and replace that with 2y 2L prime plus 1. And that's when we get when L is equal to L prime. That means we get rid of this sigma as well and set L equals L prime. Okay, and that is what we get for this. Now we can move all the terms to the other side except L prime, meaning that for this I can write two L prime plus 1 by 2. For this one, I get 1 over r to the power of L prime minus 1. And for this one, I get 1 over 2L prime plus 1. Okay, so this is how we can find all the L values. Of course, this side can be simplified a little bit. The first term can be cancelled out with the numerator of third term, so I can get this and this and make everything 1 over 2 power to the power of L prime minus 1. And these are the L values that we want to find. Okay, so these AL values computed based on sigma theta and Legendre polynomials here within that integral, combined with these equations, is give us the inside and outside electric potential in a way that it definitely satisfies Laplace's equation. It satisfies the continuity of electric field on the surface, continuity of electric potential on the surface and discontinuity of the electric field on the surface because of the surface charge density here. Okay, so if we have more information on the shape and type of sigma theta, we can simplify this further. If we have the general form here, this is the most simple case we can move, and we cannot move further forward. Okay, so if we look at the example from the textbook, they continued by making an assumption that sigma is something like something in terms of the cosine function or so on. And with that, this integral can be calculated and can be simplified further. Okay, sounds good? So we are out of time. I don't want to look at that special case test, but it's simple. You can look at example 3.9 in the textbook. Okay, and with this example, we finished the discussion of the separation of variables. We looked at the Cartesian coordinates, and now we completed the examples for the spherical coordinates. Any question?
For this last example, was it a solid sphere?
This example is not a solid sphere. This is a spherical shell that you
Okay.
have potential inside as well.
Okay.
If it was solid sphere, the electric potential inside would have been just 0.
Oh yeah, that's right.
I mean, electric field 0, potential being just constant. Any more questions? Oh. Okay, so if there's no question, I'm going to stop here. And on Thursday, I want to look at the multiple expansions. Okay, the next topic in chapter 3. We're going to look at the multiple expansion, and we're going to then focus on dipoles and electric dipoles, which are very interesting and useful topics. Sounds good? Okay, so you guys enjoy the rest of your day. Later today, I'm going to send you a list of problems for chapter 9 that you will be working on until your midterm. Okay?
Good.
When did you say you're gonna post them?
Later today.
Oh,
Then
okay.
just write the email and choose and polish that a
Gotcha,
little
gotcha.
bit. Send it.
Thank you.
Can
Okay.
you say
one.
chapter 9?
No, chapter 3.
Oh,
If you want to study chapter 9, I don't stop you, but if you're not there yet. Yeah.